you could make all of the information that's being sent between the computers public. You could literally post it in the newspaper and it still wouldn't make a difference. So you don't need to like waste energy on preventing the hacker from like knowing what's being sent. You could literally tell them what's being sent and it won't make a difference. They're still not going to know your password.
Let's roll. Sohail, how long have we been flatmates?
2 years, I would say, is the official number.
Yeah, and we've known each other for 3 years, right?
Yeah. I met you at jiu-jitsu even before I formally moved into my first apartment when I was just temporarily visiting Poland for this like 10-day stay. You were at jiu-jitsu.
Yeah, that's how we met. And it's funny that we've had the kind of conversation that we are going to record about cryptography years ago. And since then, you know that I had the podcast, but we never sat down to record it, though I had the intention. And I appreciate that your field is not cryptography. You have studied math, and I would like you to also elaborate on what field of math. You have told me 1,000 times, but I have forgotten. But you were tangentially interested in cryptography, and you studied some of the cryptography algorithms and technologies, if they are the correct words to use here. If I'm not mistaken, RSA and SHA-1, and we had some long conversations about that, and that helped me understand some of the basics better. I think when I met you, it was before ChatGPT, before my before I met ChatGPT, so so much of the basis was built there. So let us know about your background, what field of mathematics you're working in, and how you got interested in cryptography and SHA-1 and RSA. I think these were the ones that you studied, and if there is something else, correct me.
Yeah, so I guess generally the fields I do research in right now, I mean, firstly, I guess I did my PhD in ergodic theory, dynamical systems, Ramsey theory, and ergodic Ramsey theory, so like connecting these two fields. And now I'm still doing research in these fields, and I've been getting into some other fields as well, like parts of group theory, representation theory, I guess entropy, which is another aspect of dynamical systems, and yeah, functional analysis. I
And
guess
can
those are all
you
of the like buzzwords of mathematical topics that I work with. But previously, maybe when I was undergrad or something, I did do some reading about cryptography because I was interested in it. So I've learned about it. I've never done research in it. I wouldn't call myself expert by any means, but I know some of the basic stuff about cryptography and, maybe I don't know if this is relevant to our conversation today, but error correcting codes. It somehow feels like it's related to cryptography because it's a part of math that's, I would say, very applied, very applicable to the real world. And it was also another thing that I read, I think when I was undergrad, I read about it and it was really interesting. And I never went on to do any research about it or anything, but it's just yeah. I guess like cryptography and error correcting codes are the two parts of math that I would try to explain to a non-mathematician as to like how math can be applied to the real world
that's
in a
exactly
way
what I
that
was.
they can understand, instead of just saying some nonsense like, yeah, I do something, and then like 20 years later, some physicist is going to like do something with it, and then like 20 years later, some engineer will do something with it, and then like 20 years later, someone's going to put that in your iPhone. And like, okay, if it's like 80 years between what I do and what happens to your iPhone, you can't really connect the dots, right? Like that's a very abstract thing. But the cryptography and error correcting codes, I think, are very direct connections of math to the real world that can be explained to most people.
And how did you get interested in those areas when you were an undergrad student, right? It happened then.
Yeah. I mean, I don't know if there was anything specifically that happened that made me go like, ah, cryptography. I think it just seemed cool.
Mm-hmm.
And yeah. I do remember, this might have been a factor. There when I was an undergrad at Virginia Tech, I had a good professor, Ezra Brown, and he used to teach the cryptography course at Virginia Tech. Um so like at least I was reminded of like the existence of this topic because uh this course was offered every year. Unfortunately, I wasn't able to take it. I forgot what happened. I know one time I tried to sign up for the course and it was full because it's a really popular course.
Mm.
And I think they give priority to seniors. Um, but I mean, I graduated in 2.5 years, so I was never really a senior. So I think when I tried to do it, I couldn't, they wouldn't let me do it my first year. I had to take some more basic courses. And then I think my second year, there were just other courses that were relevant for me, like real analysis, abstract algebra. Um, and then in my third year, that's when I tried to take it. Uh, but yeah, it was just full. They just gave priority to the seniors, and then okay, I couldn't take the course. So at some point, I found some book and read some parts of it and learned some of the basics.
So you never got a chance to actually learn it in a class environment, but you
And I
learned it
guess
on your own.
right, so learned it on my own. So I read most of the book that I had at the time, um, which I could understand it. So I learned some of the theory pretty well. But I guess maybe some of the stuff I missed out on by not taking the class is I never actually wrote the programs to simulate these cryptography algorithms. So that is, I think, one of the parts of the class is like there were homework assignments that, you actually do write a program to implement the Caesar cipher, write a program to implement RSA and all of these things. And yeah, so I think that's like a cool thing to do to really understand it. I mean, I think yeah, it's been a while, but I think Ezra did used to say that you only understand it if you can code it. And I never did code it, so I suppose by his standards, I can't definitively say that I understand it, but but I would like to think that I still understand it decently well.
So
At least from a theoretical mathematician's point of view, I would say that I understand it. And yeah, so I never got into like quantum cryptography or any of this stuff, just basic RSA and introductory cryptography, so to say.
from your professor's point of view, I think I don't understand anything except for Hello World. I understand that very well. The only thing that I can code. Right. And for someone who has just a basic understanding of math and a high school understanding of math and understanding of puzzles and kind of encrypting messages as a layperson was always that you need a key that needs to be transferred to the person that is going to decrypt the message with, like Caesar cipher. You say that the alphabet is going to shift by 2 points, 2 positions, and then they have to know that
Yeah.
to be able to decipher it. When I first started to understand asymmetrical cryptography and public key cryptography, I was blown away by the fact that everyone has their own secret and they can encrypt messages based on what they know of each other, the public key, and everyone can independently encrypt the messages they receive with their own private key without revealing it to anyone. So that was just so mind-blowing to me. As someone who understood mathematics and you had a great foundation at an academic level in that, was it also mind-blowing to you? And if that wasn't, what was?
Um, I mean, I definitely thought it was cool and really interesting, but I don't think it was mind blowing because I understood it. You just
Yeah.
read the proof, and then once you understand it, it's not magic anymore, right? The reason magic is interesting is because you don't understand it, right? That's why it's magic. But once you understand it, it's math.
Mhm.
So
So from that lens, I think nothing is going to be interesting to you in the field of cryptography, because then you look at the proof, yeah, it makes sense, and then you are not blown away, it seems.
I mean, I guess maybe nowadays what would blow me away is if I was personally invested in a problem, if I was working on a problem for some years or something and I couldn't solve it, and then someone shows me the solution, then I would be blown away. So, like, at that point, even though I could read the solution and I could say I understand it, I would probably still get some feeling of magic that, like, wow, this is amazing. It blows me away because I was so invested in it and couldn't do it myself. Um, so like that can certainly happen. Uh, yeah.
Mm-hmm. Get that. Um,
But yeah, I mean, I think for most of the math I do these days, it's you just keep thinking about it over a long time, and you just keep making slow progress step by step. So by the time you finally get to the end, you've been with it for so many hours, like every part of it for so long that there is no magic. You've just been like suffering through it, and you're like, oh, thank Gauss that it's done.
yeah, I always love those references, that you named your late cat after this mathematician. So
Yes,
would you, as a kind of tangent, would you like to talk about that?
sure. So I had when I was at Virginia Tech, I was bike riding with one of my good friends at the time. I mean, he's still my good friend. He's just at Virginia Tech and not in Poland. Um, and yeah, we were bike riding together, and we saw a cat on the side of the path. So we stopped to, see this cat because it was cute. And to our surprise, the cat actually came up to us. It didn't have a collar. So as far as we could tell, we thought it was just like a stray cat or something, but it came up to us and it actually climbed onto us. It even climbed onto my friend's shoulder, and I have a video of him bike riding with the cat on his shoulder, and it jumped off eventually, but it climbed on my shoulder. Um, and we decided that the only way a stray cat would be so friendly to two mathematicians is if it was channeling the spirit of Gauss. So I named that cat Gauss. And I even have a picture of this cat while it's like on my shoulder and I have a bike helmet. And this used to be my Facebook profile picture, and I printed it on a sticker. And for a couple of years at Ohio State, when I had a calculus student score between a 95 and a 99 on a exam, I gave them this sticker. Like I put this sticker on the exam. Um, and if they got 100, I would put a sticker of Gauss. Uh, and when they got the 95 to 99 and they had the sticker of me, there was some text underneath of it. It used to say the first draft of the text said "good job!" exclamation point space meow, and I thought it was obvious, like I'm saying "good job" and the cat is saying meow. And then I showed it to a graduate student, and he said, "You should be careful. You don't want any of the students to think that you're saying meow, but then you could get in some trouble."
Really?
So,
Why?
I mean, I think he said it as a joke, but I was like, he has a point. It's better to be safe. So I edited the text. I wrote human, semicolon, good job, exclamation point. Cat, semicolon, meow. Just to really like make sure that it was clear
Yeah,
that yeah.
it is a cat, so yeah.
Yeah.
Hmm. All right, back to the discussion. Uh,
Oh,
where do you?
wait, no, sorry.
Oh,
I got so sidetracked on the original Gauss. So the point is, by the time I got my own cat at Ohio State, um, I determined that I wanted to name the cat Gauss before I got the cat, except Gauss was taken by this first cat. So, of course, that meant I would have to name my cat Gauss Jr. Um,
you can not have two files with the same name.
exactly. And yeah, I went to one shelter called Cozy Cat Cottage. They had like 50 cats or something, 50 or 60, all just like roaming around together. And most of them didn't give a crap about me. There were two that were interested. One was adopted like 5 minutes before I got there, and the other one was a special needs cat. They wanted to give her to a really good family, so they didn't give her to me because most likely because I wrote on the forum that I would be out of the house for like 10 hours a day or something, and they didn't like that, I assume. And then I went to another adoption center where they had 6 cats, and one of them, 5 of them didn't give a crap about me, but one of them like sat in my lap and purred. So I adopted that cat. I named her Gauss Jr. Of course, right? The name was predetermined, regardless of the gender. Turned out to be a girl,
Yeah.
and yeah, I had her until I think was it January 1st or January 2nd, one of the first 2 days of 2025.
Right. I will put a picture of her over here on the video
Good.
in memory of Her Majesty. Now back to cryptography. I mean, were you aware of the fact that asymmetrical cryptography was a thing? Because before Bitcoin, I was not aware that it was a thing. And even after years I was in Bitcoin, I still did not know what even asymmetrical cryptography is. Um, until recently, that I got a better understanding of it. So, were you aware of it?
I mean, yeah, that's basically what RSA is.
No, before reading about
Oh,
it.
no, I had no
Uh-huh.
idea about it until I
And
read
still you
about RSA.
weren't blown away. Oh, interesting. Because you see the proof and you see it makes sense. Okay, I kind of get it.
I mean, yeah,
Um,
maybe I guess because I didn't it is possible that if someone told me about it first and I thought about it, I was like, huh, this is really weird. This I don't understand this. That's kind of amazing. And then I read the proof later. Like, yeah, there could have been this chance, but I think what happened was I just knew nothing about cryptography, so I had no idea what to expect. And then I just found this book and I just started reading it. So then by the time I got there, it's not like someone told me some fact that I didn't understand for like a month or something before finding this book. It was just the next chapter in the book. So I just read it and then that was that.
I totally get it. So, you got to know about RSA and SHA-1, if I'm not mistaken. What else did you learn about? Of course, the
Honestly,
cipher is
you'll
not.
have to refresh me on what SHA-1 is. I don't know the name SHA-1, but if you tell me what it does, I can tell you if I
Oh,
read about it or not.
well, SHA-1 is a weaker version of SHA-256. What the difference is, I totally do not know. I was hoping to ask you about that. So, RSA is the one that you are acquainted with.
RSA is yeah, it's the one, it's the most one of the reasons RSA is like well known amongst mathematicians is that there was this really famous mathematician, this English mathematician named G.H. Hardy from the 1900s. Um, one of the top mathematicians of the time. Uh, and he said, okay, I mean, I should know the exact quote, but I guess I'll paraphrase because I don't know the exact quote. But he basically said, like, mathematics is beautiful because it doesn't have applications, and like number theory is the queen of mathematics because it really doesn't have any applications. Okay, so this is even like worse than paraphrasing. Like for sure, the quote sounds nothing like that, but that's the idea behind it. Like he really liked number theory. He thought it was really beautiful, and at the time he was very proud that there, like he thought that there would never be an application of number theory. It was just like too abstract, really just this like game for mathematicians to have fun and do something beautiful and artistic. Um, but then number theory is the foundation of RSA. It's the reason RSA works, like how you prove that it works or how you construct the algorithm is reliant on number theory. So he turned out to be, I don't know, 50, 60 years, whatever later, completely wrong. Number theory is extremely applied. Uh, you could say that, all of the security of banks and credit cards and all of the stuff is relying on some form of RSA. So it's relying on some number theory. So it's extremely applied. So this is one of the reasons RSA is very well known um in the mathematical community.
And refresh me on the abbreviation Rivet, Shamir, which is the famous Ari Shamir, right? And
I should know, but I don't know.
oh,
The only thing I can tell you is the S from RSA was at China at the institute that I'm going to in 4 days. He was there like 2 years ago, and he got $1 million prize. Just like as a general like respect for his mathematical career and all of his various accomplishments, including RSA. Yeah.
he really deserves it. I think even our authenticator apps, Google Authenticator, Microsoft Authenticator, I think they are also built upon RSA. Is that so?
It's possible. I don't know specifically, but I mean, I would assume that anything that uses uh, passwords and security in general probably uses a form of RSA.
Mm-hmm.
Yeah.
And how does that work? For some, as if you're explaining to a 6-year-old, maybe a bit older.
So yeah, I can start. There's this classic explanation. Um, I don't know who to attribute this to, but I've heard many people describe it this way, so I also like to describe it like this. Uh, so let's say I want to send a suitcase to someone. I put some physical objects in a suitcase, and I want to send it, like, maybe I want to send it in the mail to my mom. But it's some really private stuff that I'm sending her, and I really don't want anyone else to see it or know what it is. It should be a secret.
Your love letters.
Yeah, of course. So then I put a lock on the suitcase to make sure that no one can open it. And then I send the suitcase to her, and I know that no one can open it because I locked it. And then she gets the suitcase, and she can't open it because it's locked. So that kind of sucks, right? The lock was somewhat counterproductive. But then what we do instead is, this is where the magic of RSA comes in. She doesn't immediately try to open the suitcase. She knows she can't open the locked suitcase. So she also puts her own lock.
Oh, so your mom is the receiver. She's
Yeah,
not
she's
just the
receiving.
intermediate. Okay.
Yeah. I'm sending it
And
through
she
the
should
mail.
be able to open it.
Right.
Mm-hmm. So it is no secret to her. It is something that needs to be held secret from the people in the logistics until it gets to her.
Yeah, like maybe someone attacks the mailman and steals the suitcase, and I don't want them to know what's inside.
All right, got it. Mm-hmm.
So she gets the suitcase, and she gets it safely because I put a lock on it, but she still can't open it. So then instead of trying to open it, she just puts her own lock on top of the suitcase as well. So there's now 2 locks on the suitcase, which seems like it's counterproductive because now it's even harder to open because there's more locks.
Right.
And then she sends the suitcase back to me. And again, as it's coming to me, it's safe. Nobody can open the suitcase because now it even has 2 locks rather than just 1 lock. And when I get the suitcase, I have the key to my lock. Or, maybe it's one of those locks where you have like the 4-digit password or whatever. I know how to open my own lock. So I just open my lock and take it off and throw it away or whatever. And then my mom's lock is still on the suitcase. So I put it back in the mail and I send it back to her. And again, it's safe. Nobody, like, if they steal it from the mailman, there's still a lock on it, so they can't really open it. And she gets it back. And now my lock has been removed. And it's just her lock, and she knows how to open her lock, so she just opens it, and then she can open the suitcase. So the point is, on the one hand, it's a bit annoying that rather than just sending it to her once, it has to go back and forth 3 times rather than 1 time. But now it's completely secure. At no point could anyone open the suitcase. And I never even had to, like, provide any information to my mom, right? It's not like if I put my lock on it and it has some password, I can just call my mom over the phone and tell her the password verbally, because maybe the hackers are going to hack my phone call and they'll hear me tell her the password. and then they'll attack the mailman, and they've already stolen the password from the phone call, and they'll open it up. But right, so there's like a weakness there. But with this double lock procedure, like I don't need to tell her anything. It's just whatever's in the suitcase. That's it. There's no other communication between us, so there's nothing else to intercept. So that's where the security is coming in.
That was a great explanation of it. I hadn't dug much, dug deep into RSA. I had read about it, but the explanation was not this clear. Now, let's make it more advanced. How this happens in a mathematical world? Because to me, it is like sending something, getting something, sending a message, receiving a message. And this is not something defined in the mathematics. So how does that happen? Or at a that was a high level understanding of it.
Yeah.
If we want to go lower without losing me, what would you say?
So the point is all of the stuff we have on electronics these days, we're sending bits, we're sending strings of zeros and ones to each other. So when you want to like log into the bank, like you have a account at the bank and they have a website, and you want to log into your account to check your balance, maybe send some transfers or something, you type a password into your computer, and then that password, it needs to be sent to the servers where the bank website is hosted. So the information that you put into your physical computer gets sent through the internet to some other physical computer where the bank website is hosted. And again, this is the analog of like the mailman. Is when you're sending this data, you don't know who else can try to like intercept the network and like see what data is being sent. So if you just directly send your password to the bank, anyone who can look into that, I don't know what the term for this. I want to say like that internet, but that's not really a
That
official term.
package, they call it.
Yeah. I mean, I guess maybe the other, you could just say like, if you just send it directly, a hacker could see what you sent, and then they can know your password, and then they can just log into your account, right? So we want to, right now, of course, you can try to like say like, oh, it's so secure that it can't be hacked, but what does that mean? So how can you make it so that it can't be hacked? I want to say the best way, but maybe let's just be modest and say like a way to make it not be hacked is to say that you could make all of the information that's being sent between the computers public. You could literally post it in the newspaper and it still wouldn't make a difference. So you don't need to like waste energy on preventing the hacker from like knowing what's being sent. You could literally tell them what's being sent and it won't make a difference. They're still not going to know your password. That's what we want to do. We want a system that is so good that even all of this intermediate stuff, if we literally put it in the newspaper, they still can't figure out what our password is. So we don't have to worry about like, if they look at it, like, yeah, go ahead, look at it. I'll put it in the newspaper and still my password is safe. So how do we do this? I guess I'll do this twice, once somewhat abstractly, and then maybe I'll get into the details. So I have my password, and of course it turns into a bunch of zeros and ones. So it turns into like a number, basically. And then rather than sending that number directly through the internet to the servers of the bank, my computer will first apply a function, a transformation, and convert the number into a new number. And then that's the number that gets sent to the bank servers.
That can be published in a newspaper without it making sense to anyone.
Exactly. Because nobody knows what transformation I applied to the original password other than my computer. So when they see the number that's being sent, it's meaningless. Because if you don't know what transformation was applied to give you that number, you can't undo the transformation and get back the original number. It's just some number, right? So it's meaningless. Now, of course, that means when the bank receives this number, it's also meaningless. They have no idea what that number is. But what they do is they apply their own transformation on top of this number as well. So at this point, the number has been transformed twice, and then they send it back to me. And I don't know what transformation the bank used, but I'm just going to undo my transformation. And this is where the math comes in, because what's happening is it was my transformation, and then the bank's transformation, and then after that, I want to undo my transformation. And in general, it's hard to do, right? Because there's some, in math, we use the term commutativity, that the order doesn't matter. So like, if I just applied my transformation, then I could directly undo it. But if I apply my transformation and then the bank does something to it, who knows what, it's not obvious that I can still undo my transformation without knowing what the bank did. So this is a non-trivial step, and this is where all of the math comes in, is how to pick the transformation so that the order doesn't matter. That regardless of whatever the hell the bank did, I can still undo my own transformation without knowing what the bank did. So I undo it, and now all that's left is the original number with the bank's transformation on it, and then we send it back. Again, if they intercept this, it's just some number. No one knows what transformation the bank is using, so if they get the number, it's useless. It goes back to the bank, they just undo their own transformation, and they can see the original number that I entered into my computer, and they'll say, is this the password? Yes, it is, and they let me in.
Oh, Jesus, it is so much more complicated than public key cryptography. When you encrypt something with someone's public key, here you put your lock on it, it goes there, they put their own lock on it, it comes back to you, you remove your lock, and the order does not matter. So the magic is actually here that it is a kind of function that is irreversible. By knowing the answer, you cannot get to the function, to the initial value, if that is the way, correct way of putting it. And
Well,
at the same time, it is the order does not matter.
If you know the function and the value it puts out, you can get back to the input. But the point is, if you know the output and you don't know the function, then you can't get the input.
And there are so many of such functions.
Exactly.
That you randomly pick one of these functions as your function.
Yes.
And the bank randomly chooses one of these functions
as their own function. Yeah.
Oof. So there are so many difficult.
And for each interaction, they can pick a new function. They don't have to use the same one each time. So like when I enter my password to log in, I pick a function, the bank picks a function, and then 10 minutes later you log in, you pick a function, and the bank can pick a new function. And then tomorrow I log in again, I pick a new function, I don't have to repeat either. And then the bank also just picks a new function. So there's no need for repetition. It can just be a new function every time. Maybe you can repeat it if you want to, but you don't have to.
And these functions are irreversible. It is not like...
Well, I don't know what you mean by irreversible. That's not a precise term.
All right. Because
so
if you know the output and you know the function, you can go back, in fact. All right. Yeah.
So the function is I guess the function is reversible, or we would say invertible. It has an inverse. But the problem is, if you want to reverse it or invert it, you need to know what the function is.
Mm-hmm.
If I give you a number and ask you what's the inverse, that question makes no sense. It's not a well-defined question. I need to say, here's a function, here's the output, now reverse it, give me the input. That question makes sense. You can try to solve that question. But if there's no function and there's just a number, you can't even ask what is the inverse. It just doesn't make sense.
So what features, what properties should these functions have, and how are they chosen? From which kind of space are they chosen?
So I can just directly tell you what the functions are. So first, I don't know, have you heard of this clock arithmetic? That like
Oh, yes.
on a clock, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9,
To
10, 11,
12,
12,
and then
and
again
then
1.
back to 1, right?
Mm-hmm.
So it doesn't go to 13, it just wraps around.
Yes, yes, yes.
So this is also called modular arithmetic in math, and this is the beginnings of number theory, is studying modular arithmetic, where you pick a number. It doesn't have to be 12, right? 12 is just the clock example because that's what we have in the real world. But you can pick any number you like and say that, we're going to go from 1 up to that number. But then if you try to increase it by 1 more, you're going to go back to 1. It just wraps around. So it's like a finite set on which you have some addition and even some multiplication. So like any number, for now, let's just fix the 12 for the clock example. But like if someone gives you a number like 1,000, you can identify that with a number in the clock world, where you just divide by 12 and you take the remainder. So if you divide 1,000 by 12, it's not going to go in evenly. Well, it's going to be like 960 is 80 times 12, and then 36. So like 1,000 is 83 times 12 plus 4. So if you try to divide 1,000 by 12, you get a remainder of 4. And then, okay, just to make it a little bit more, I guess, mathematically standard, I want to make a small adjustment. Rather than making it go from 1 to 12, I'm going to make it go from 0 to 11. Because usually mathematicians like to start this clock arithmetic or this modular arithmetic from 0, because 0 is very significant and useful to have. So I'm gonna do that 0 to 11. So now the number 1,000 is identified with 4, because you just keep dividing out the 12s until you get something left, and something between 0 and 11, and whatever that is, that's your new number. Right? So like if you had 12 million, that just turns into 0, because 12 evenly divides into it. 13 just turns into 1. 26 is 2 times 12 plus 2, so that turns into 2. So any number, you can identify it with something between 0 and 11. And then again, the fact that we started with 12 here is not important. You could start with any number you like, 17, 1,000, 1 million, billion, and you can repeat everything I just said. And in this fashion, right, we get this modular arithmetic. So addition is well defined there. You can add 2 numbers. So like if you add 7, let's go back to the example of 12. If you add 7 and 8, you get 15. And 15 is 12 plus 3, so it turns into 3. So 7 plus 8 is 3 in this clock arithmetic world. And 7 times 8 would be 56, and 56 is 48 plus 8, so it turns into 8.
8. Mm-hmm.
Right? So you can define addition and multiplication in this clock arithmetic world. And then, right, so now that we have this, the other thing we can define, now that we've defined multiplication, is exponentiation. So like raising to the power of 2 or raising to the power of 3, right? So what does it mean, x squared? To square a number is to multiply it by itself. Well, if we can multiply in this modular arithmetic world, then we can multiply by, a number with itself. So we can square and we can cube, right? So if you take like 6 mod 12, then 6 times 6, 6 squared is 36, which is 0.
Mm-hmm.
And then 6 cubed is 6 times 6, so 0, times 6 is still going to be 0,
Mm-hmm.
right? Or like 1 squared is 1 times 1, it's still 1. 1 cubed is 1 times 1 times 1, still 1. Or 2, right? Like 2 squared is 4, but 2 to the 4th power would be like 2 times 2 times 2 times 2, which is 16, which turns into 4, mod
Mm-hmm.
12. So, right, the point is the modular arithmetic world has addition, multiplication, and exponentiation with these integer powers.
Because whenever we have multiplication, we kind of have exponentiation
Yeah, if the
followed.
multiplication makes sense, then you have this exponentiation as well.
Mm-hmm.
Now, there is a important result in math. It's very classical now. It's called Fermat's little theorem.
Yeah.
And it's the basis of RSA. It says
Oh.
if you take a prime number, right, so 12 is not a prime number. 12 is 2 times 2 times
And the
3.
reason that you started with 11 was that?
Because rather than 1 to 12, I wanted to start with 0.
Oh,
So 0 to
right,
11 is
right,
still
right.
12 numbers.
Mm-hmm.
It just
Okay,
starts
okay.
at 0 rather than
Okay,
1.
got it. Mm-hmm.
But if we take a prime number such as 11, which would correspond to the like mod 11 means we're working with the numbers 0 up to 10. Right. So you take a prime number, and Fermat's little theorem says if your prime number is p, then any non-zero number you take mod p, if you raise it, sorry, actually let me start this again. I can make a slightly easier statement. Well, okay, you know what? Yeah, I'll give the easy statement and then the slightly harder statement. So the easier version is you pick a prime number p, and any number that you take mod p, if you raise that number to the power of p, you get back the original number. So again, let's say p is 11,
Mm-hmm.
because 11 is prime. So 1 to the power of 11 is 1. Okay,
Yeah.
that's easy, not a surprise. 0 to the 11 is 0,
Mm-hmm.
also not a surprise. 2 to the power of 11, mod 11, is going to be 2. Now, that's not obvious, and that actually takes some work, right? Now, because 11 is small, you can directly calculate it, right? Like 2 to the 11 is 2048. You can just put that into a calculator. So if you just put 2048 divided by 11, you'll get that the remainder is 2. And then 3 to the 11, that's already big. I guess you could probably still do that with a calculator, but I don't know what that is off the top of my head anymore. But 3 to the 11, mod 11, is 3.
Ah.
And then
So 4 to the power of 11, and then the result of that, mod 11, is that number.
is 4.
Is 4.
Yeah.
Mm-hmm.
Same with
Whatever 4 to the power of 11 is, mod 11, it is going to be 4.
yes.
Mm-hmm.
And all the way up, same for 5, 6, 7, 8, 9, 10,
Yeah.
and even 11, right? 11 to the 11, mod
Uh-huh.
11
Up
is
to
still going to
11
be 11.
itself.
No, even you only need to check it for 0 to 10 because that's all that like really exists in the mod 11 world. Everything gets identified with one of the numbers 0 to 10. But it's still, even if you don't want to do this identification that mathematicians do, right? Because it's kind of like abstract, so to say, you could just do it directly and it's still going to make sense. Like if you take 15 to the power of 11
Mm-hmm.
and you reduce it mod 11, you will get 15 mod 11, which is 4. 4 and 15 are the same mod 11, right? But yeah, so 15 to the 11, if that's gonna take a long time to compute if you try to do it by hand. But yeah, it'll just turn out to be 4 when you reduce
I
it
think
mod
on a
11.
normal calculator, you wouldn't be able to even display the number.
Yeah, probably. It probably would be too big for a normal calculator to display. Yeah.
Mm-hmm.
I mean, but yeah, even if you want to make something too big for, uh, you know, modern computers, you could just take a gigantic number with hundreds of digits and multiply it by 11 and then add 1. So you have like an expression for the number. And then this number raised to the power of 11, mod 11 will just be 1. But if you wanted to literally calculate it without using Fermat's last theorem, just like raise it to the power of 11, if the original number was big enough, then it'll be difficult for the computer to compute.
So where
I mean,
does
maybe at the
Fermat's
end of the day,
theorem?
I guess it's maybe not that bad, but because it's like linear time, but it's still, you know, not that easy. Sure.
So where does this Fermat's conjecture that then changed into Fermat's theorem come into the picture when we talk about
Well,
RSA?
I didn't mention Fermat's conjecture, so let's not go there.
Ah,
Just because let's just
uh-huh.
stay
So
on
this
Fermat's
is
little theorem.
Fermat. Okay, okay, okay.
Yeah,
Yeah, right, right, right.
there is something called Fermat's last theorem.
Mm-hmm.
Um, but let's not go there because it's not directly related to this.
All right. I
So
thought that it was actually the expression of that. All right. So good
no, so
that it is clarified now. Okay,
yeah,
right.
yeah, this is called Fermat's little theorem. Yeah. Um, and yeah, this theorem it's taught in I would assume any undergraduate course in number theory. And a lot of like if you do like high school math competitions or something, then the books that prepare you for these competitions usually have something about this in them. Or it's expected that you know this to solve some of the problems that appear in these competitions and stuff. So it's a very classical thing. It's accessible to high schoolers or just people interested in math. Like even if you're just like a hobbyist, you could go to Wikipedia and read about Fermat's little theorem and understand it if you just put some time in to read it. It's very accessible. You don't need to be a professional mathematician to understand this. Or yeah, you might have to put in more work, uh, but that's fine. It's still very accessible.
Right.
Um, now, right. So now there's an equivalent form of Fermat's little theorem, that I'll state now. It was the thing I was going to state at first, but it's because it's slightly more complicated, I decided to save it for later. Um, so now we take our prime p and we say that if you take a number mod p that's not 0 and you raise it to the power of p minus 1, you're going to get 1 mod p.
Mm-hmm.
So this is more or less the same as the previous version of Fermat's little theorem that I told you. Mathematicians would say they're equivalent in that if you know one of the two statements, you could easily prove the other statement and
Mm,
like much more quickly than if you just try to directly prove either of the two statements independently from the ground up.
correct. Mm-hmm.
Um, so again, this is slightly more cumbersome to state because we say the number is non-zero, so there's an assumption, and rather than p, it's p minus 1.
Yeah.
And since we're kind of just like talking in the air and not writing, it's annoying to have a few extra symbols. But yeah, so just to repeat myself, the equivalent form of Fermat's little theorem is that you take a prime p and you take a number that's, when you reduce it mod p, it's not 0. If you raise that number to the power of p minus 1 and then reduce it mod p, you're going to get 1 every time. All right, so again, going back to our example of p equals 11, it means if you take, we throw out 0, and now if you take any of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, any of those numbers, and you raise them to the power of 10,
10, okay. P
then
minus 1.
you're going to get 1 after you reduce it mod 11.
All right.
And yeah, so this is used in the cryptography in RSA because basically what it means is the number. So what happens is I have my password that I put into my bank website on my laptop. It turns into some string of zeros and ones. Okay. And of course, like most banks, they have some limit, like your password can't be more than 32 characters or whatever. I don't know, maybe there's some crazy bank that says you can have like a 64 character password,
Yeah.
but they're going to have some limit, right? Okay. And I guess they're probably all using UTF-8. So each letter turns into 8 zeros and ones, 8 bits. So if we had like a 32 limit digit cap, 32 character cap on the password, times 8 is going to be like a 256 bit cap on the size of your password after you convert it into UTF-8. So after you convert it into a number of zeros and ones. And now you pick any prime that you like bigger than 2 to the 256. So it's going to be a fucking huge prime, but you can pick one. And for, the bigger the prime, the better, the more secure RSA is going to be, generally speaking. Some of the people who like really specialize in RSA can maybe tell you like, actually, there are some additional properties other than the size that can improve the security. Again, I'm not one of those people. I just know the basic form. So for the most basic form of RSA, the bigger the prime, the better. So you just pick some really, really big prime. And then you put in your password, which is some 256 digit binary number. And what you do is,
So you assume that my password was 32 characters long?
yeah, I mean, you could have the empty character as well, right? Like if it's 8 characters, what that really means is 8 characters plus 24 copies of the empty character.
Ah,
So,
okay. So everything turns into 256 bits.
Yeah.
All right.
So this is like a standard mathematical assumption that you can always put empty character at the end.
So even if my password is mo1234, it's going to add the rest to make it 32.
Yeah.
All right.
Yeah. So now we put in the password, and what happens is we pick some number, and again, maybe I'm skipping a couple details here, but I can come back to it later. For now, let's say you pick a number, and you raise your password. You view your password as a number modulo p for this really big prime p. And this prime p, it can be published in the newspaper. It's public knowledge. Everyone knows what the prime is. The bank knows, all of the hackers know what this gigantic prime number is. Now, when you enter the password, you have a number that only you know. You don't even tell the bank.
Yeah.
You raise your password, viewed as a number mod p, to this power. And then you reduce it mod p, again, after you raise it to the power. And that's the transformation. The transformation is exponentiation to some power of your choosing. And then you send that to the bank. So now, if the hacker steals the number that you sent, it's useless because they know that you raised something to some power, but they don't know to what power, because you didn't tell anyone what power you raised it to.
But you said that this prime number can be in the newspaper.
The prime number can be in the newspaper, but the power to which you raised
Oh, right,
your
the power.
password
Right. All right.
is not going to be published. That's like your personal
And the
secret.
power is p minus something non-zero up to p minus 1?
Correct.
All right.
Yes. Something between 1 and bigger than 0 and smaller than p minus 1.
P smaller than p minus 1, not
Right.
including.
If you actually make it p minus 1, it'll just turn into 1. And you can't undo that, right? If everything turns into 1, you can't undo it and figure out what you started with.
Right.
So this is getting into one of the details that I'm skipping.
Okay, got it.
Again, we can come back to that in a second. For now, let's just say anything bigger than 0 and smaller than p minus 1. So you raise it to that power and you send it, and it doesn't matter if some hacker steals it. They can't figure out the original password because they don't know what power you raised it to. So now, the bank gets it. They also don't know. They're also going to raise it to some power of their choosing, and then they'll send it back to you. And when you get it, you don't know what power the bank raised it to. But here's the thing. You can still raise this number to another power. And you can pick a power to raise it to such that together, the first power you raised it to multiplied by this next power you're raising it to is the same as raising the number to the power of like either p minus 1 or like 2 times p minus 1, some multiple of p minus 1. And this is important because, right, whatever number you started with, when you raise it to the p minus 1, you get 1. That's Fermat's little theorem. Because, of course, we're starting with a non-zero number, right? Your password, the bank is not going to let you pick the empty password as your password. And the empty password is the thing that's going to go to like 0000, and yeah, that's out of the game. So if you raise your password to the p minus 1, it turns into 1. And of course, like 1 squared or 1 cubed is still 1. So if you raise your password to the 2p minus 2 or 3p minus 3 or 10p minus 10 or whatever, it's still going to turn into 1. So basically, whatever power you picked in the first place, you pick another power such that together when you multiply them, it's divisible by p minus 1. And then what that means is when you do both of the powers together, your password to that both of the powers turns into 1 mod p. So it goes away. And all that's left is your password to the power of whatever the bank did.
And the bank knows what they did. Right.
So they can do the same thing, and they can undo their password. They can make it equal to, rather than divisible by p minus 1 exactly, they don't want to make it go to 1 and destroy all the information. That's useless. They want to multiply it so that when you divide by p minus 1, you get 1 as the remainder. And then all that's going to be left is the original password. And the thing, this commutativity I mentioned earlier, it's being used in the fact that the order in which you do exponentiation doesn't matter.
And one of the functions that is like that is these modular functions.
Well, it's the exponentiation function. Right?
Okay.
So if I pick, like, let's say some numbers. So first, my original number is 2, and then I have some powers, 3, 4, and 5. If I do 2 to the power of 3, and then that to the power of 4, and then that to the power of 5, that's the same as doing like 2 to the 3 to the 5, and then to the 4. Or 2 to the 4 to the 3 to the 5. It doesn't matter what order you exponentiate the 3, 4, and the 5, the result is the same, right? So that's a property that's being used here.
This exponentiation is one of the ways it can happen.
Yeah.
So there are several ways of doing this RSA stuff, yeah?
Yeah. So
And it matters that I use exponentiation and the bank uses exponentiation, or we can use two different functions.
no, for this to work, the version that I explained, it's important that you both use exponentiation,
Right.
right? Because
Otherwise, it would
I
have
want this
been wow.
commutativity property.
Right, right.
The fact that I can undo my own exponentiation without knowing what the bank did is because all of our exponentiations commute with each other. That we can change the order and it all works. So if I exponentiate and then the bank adds 5 and then they send it back to me, I can't undo the exponentiation anymore. I'm fucked.
Because you don't know that they added 5.
Yeah, the add 5, that's gonna mess up everything. But yeah, because like if you square a number, add 5, and then cube it, that's not going to be the same as like squaring it and then cubing it and then adding 5.
Yes.
Right? That the order actually does matter.
Yeah.
And that's a problem. But as I said earlier, if you just do like cube it, raise it to the 4th power, raise it to the 5th power, it doesn't matter in what order you do those things, it all commutes.
Mm-hmm. Awesome. So that is the basis of RSA. What is this fascination with prime numbers that in Bitcoin also what we use is prime numbers? And I think there are 2 prime numbers that are multiplied by one another, and then the result is the public key, something like that. Anyway, whatever it is, there's prime numbers there. There's prime numbers in this RSA and this exponentiation stuff that you said.
Right.
What is
So
this fascination with prime numbers? What's the...
this is relating to that detail that I skipped in the previous explanation. So I mean, firstly, the general fascination with prime numbers is Fermat's little theorem. The fact that what I described to you worked, this procedure with exponentiation, relied on Fermat's little theorem. The way that I undo my own exponentiation is to do another exponentiation to make both of them equal to 1, so it goes away. Because when you multiply by 1, that's the same as doing nothing. And that only works because of Fermat's little theorem, which is proven for prime numbers. It's only true for prime numbers. It's not true for composite numbers. Right? For example, I said this in passing earlier. 6 mod 12 is not 0. But 6 squared mod 12 is 36 mod 12, which is 0.
Yeah.
So if you raise 6 to any power that's 2 or bigger, mod 12, it's just going to be 0.
0.
Right? So you cannot raise 6 to some power and get 1 mod 12. That's impossible. Even though 6 is not 0 mod 12. So this is showing you that there's some, Fermat's little theorem does not work for composite numbers. Now, okay, are there related theorems that are kind of similar that work for composite numbers? Yes, but I guess it's maybe I don't want to get too far sidetracked and go there right now. I feel like this is already a pretty dense conversation, given that we're not even writing anything. We're just kind of speaking.
Yeah, I really feel the need to look at Fermat's little theorem and understand it better.
Yeah.
And actually, there were some stuff about RSA that I didn't know before, and now I know.
Oh, and I should say, in addition to Wikipedia, I'm 90% sure that the YouTuber, keep forgetting if it's 3 brown, 1 blue, or if it's 3 blue, 1 brown. But there's this YouTube guy who makes videos that explain math ideas for a general audience. And I'm pretty sure he has a video about Fermat's little theorem. So in addition to Wikipedia, you can try to find him.
Yeah, if
or
I
maybe I'll
find
look it up
that-
after this podcast and you can like put a link under the
Yeah.
episode, and he generally, I've watched many of his videos. He generally does a very good job of explaining uh important mathematical ideas in a accessible fashion with a very good video that I guess he makes his videos with Python or something. Like he programs them, and
Yeah.
they're
Also.
good. It's an impressive channel.
Mhm.
Um but again, also I should actually explicitly state that I really like Wikipedia for math. I frequently use Wikipedia for math, and I think it has a good explanation of Fermat's little theorem. So that those are the two sources I recommend.
Since I am on the left side of the IQ distribution, I appreciate videos. They will help me understand things better than pure text.
Yeah. Um. But anyways, right. So I told you one of the reasons we want a prime number is to use Fermat's little theorem. That's really important. Now, the other reason, you were saying something in Bitcoin about like a product of two primes, blah blah blah. Um, right. So now I have to tell you the detail that I skipped in the RSA. The detail I skipped was when I said you exponentiate to any number you want. That's the problem. You can exponentiate to almost any number you want. The numbers that you have to avoid are the numbers that have a common factor with p minus 1. So even though p is a prime, a big prime, p minus 1 is not going to be a prime.
Mhm.
Because at the very least, it's going
Yes.
to be divisible by 2,
Yes.
right? So there the thing is, like, if you take some number and you let's say this, um
A few moments later.
sorry, I got sidetracked for a second. I'm thinking I'm wondering if I made one other mistake earlier when I was describing this to you. I think I did, but I don't know if we want to go back and hash it out. I Whatever, we'll leave it.
Mm-hmm.
I think if a mathematician was watching, they'll probably catch the one mistake I made earlier, but if not, I think the general idea got through, so I'll let the one mistake sit
Mm-hmm.
there. Um but going back to this thing, the current topic, p is a prime, p minus 1 is not going to be a prime. So uh we take our number, and if we square it, then 2 divides p minus 1. Because, of course, right, when I say p is a prime, we're assuming it's a big prime, so it's not 2. And any other prime is going to be odd. So if we were to, for example, square our number, we pick 2 as our exponent, then any other exponentiation we do after that, it's always going to be a multiple of 2, right? Because it's like you first exponentiate by 2, and then you exponentiate by anything else. You multiply these together, so it's exponentiating by something even. And what that means is no matter what you do, no matter how many times you exponentiate, your exponent is never going to be 1 modulo p minus 1. So, and that's what we needed in order to get the end result. Like for the bank to actually get back to the password that you punched into your computer, the end result of all of these 4 multiplications has to be 1 modulo p minus 1, and then you'll recover the original number.
Mm-hmm.
But if you throw in a 2 in there, you can never get back to 1. You'll always be divisible by 2.
Yeah.
And it's the same for any other number that shares a common factor with p minus 1. If you share any common factor with p minus 1, no matter how many more exponentiations you do, you're going to continue to share that common factor with p minus 1. And that's going to break the process. So you can only pick numbers for the exponentiation that are co-prime with p minus 1, that share no common factors with p minus 1. And this
That's
is
not
why
co-prime. Okay.
they want p minus 1 to have a small number of prime factors, because then more numbers will be co-prime to p minus 1, and that means there's more possibilities for the exponentiation, which makes it harder for the hackers to guess what exponent you used. And of course, the smallest number of prime factors you can have is 2. You can just have it be a product of 2 primes. Or maybe like 3 primes.
Yeah, maybe getting almost to the end, I want to ask about this. The possibility of a hacker in the way trying different combinations and getting to that, or seeing both your message and the message that bank sends to you and the message that you send back to the bank after you have undone your exponentiation.
Yes.
What are the chances of a hacker intercepting the messages, being able to crack your code?
Okay, so the short answer is it's still extremely low if they just have these 3 messages. That's not really much better than just having 1 message. Because also keep in mind, even though it's 3 messages, now they need to guess 2 numbers. They need to guess your exponent and the bank's exponent. So it's really not any easier. There is research about, like, if you and the bank always use the same exponent, then how many messages would they have to steal before they could find out your exponent and the bank's exponent? So this question has been asked and has been studied, and there are answers to it that I don't know right now, but
there's a possibility if you do not change
right.
the
So if
power
you
to which you exponentiate, yeah?
Yeah, if you keep using the same exponent and the bank keeps using the same exponent,
After enough
and the
number
hacker
of
intercepts
encrypted.
everything, eventually they'll be able to put the pieces together and figure it out.
Okay. This actually answers something that I heard when I was a teenager. When I was a teenager, and I heard this scenario that if they have enough messages, then they can crack the code. So they have been talking about this.
Yes.
All right.
And then, so I think this is one of the reasons why the new thing in, I think, the new thing in cryptography, again, this is kind of where I'm not the expert, but the next level of complexity after modular arithmetic is elliptic curves.
That's Bitcoin. How we get to our...
Right. So, and for all I know, maybe a lot of the modern banking systems and stuff are already operating on elliptic curves. That's entirely possible. But the point is, elliptic curves are another mathematical system where we can have a version of this exponentiation, where, like, I exponentiate, the bank exponentiates, I exponentiate again to undo the first one, and the bank exponentiates to undo, right? They can do this whole process, but rather than doing it mod p, they do it over the mathematical system of elliptic curves, and it's supposed to be more secure. Maybe one of the reasons could be that it's, they could intercept more messages and still not hack it. But I should be careful not to say too much here, because I haven't studied the elliptic curve cryptography in detail, so I really don't know, other than just the abstract nonsense that I said right now.
Yeah, I appreciate what you said about RSA and how the earliest cryptographies came into existence. Maybe that was the first application of number theory, or was it not?
To the best of my knowledge, I think it was the first application.
So
I mean, unless you want to say something stupid like, oh, a clock is modular, so like clocks are applications of number theory. I mean, I guess in theory you could say something like that, but I think clocks existed before number theory existed, so that's probably not a good example. So I think RSA to the best of my knowledge, that's the first serious application of number theory.
How many times over that person who in 1900 said that?
G.H. Hardy?
J.H. Hardy. How many times over has he been proven wrong after he was proven wrong by RSA?
That's a good question. So I guess you're asking what are the other applications of number
Yeah,
theory?
that's
Yeah.
that's yeah. You actually
So-
cracked the code.
I think I guess elliptic curves would probably be considered a part of number theory.
Mhm.
Now, so of course, elliptic curve cryptography is, you could say, another application of number theory. I don't know if you want to call it another application or like an extension of the first application, but there's something there. I've heard of applications of number theory to physics, just in some like articles that maybe I read them and forgot, or maybe I just like read the title, some like quant article or something. But I can't tell you anything meaningful there. I just vaguely know that some parts of number theory connect to physics. Yeah, I don't know. It's a good question. I wish I knew more applications of number theory, but I think that's all I can say for now.
Yep.
Something you might we do have a professor at our university at Adam Mickiewicz, Bartosz Naskrensky. He is a number theorist. Most of his papers are published in number theory, in the topic of number theory, and he knows a lot about the applications. He even helped film some of the videos at the cryptography museum that we have in Poznan.
Oh, nice.
And yeah, he knows a lot about the elliptic curve stuff and quantum cryptography. So, depending on how far you want to go with this podcast, you could try to set something up with
That's
him at
awesome.
some point.
Yeah. That would be a great idea if I can do that. Yeah, definitely. Especially because Bitcoin is all about elliptic curve cryptography. They call it ECDSA.
Yeah.
That's the one that is used. And the reason that it is used and how we use that, because a curve, there's a line of so many numbers. How do we choose one number, and how do we get to the same results? That's so complicated for me to wrap my head around. All right, and back to this gentleman Hardy. What other not dogmas, strong opinions do you think are going to be broken in the future? That he had this strong opinion that there is not going to be any application. It's just a form of mental exercise for mathematicians, but it became the most groundbreaking application in the in this in the modern world, I would say. Because I am all blown away by cryptography and what it has made possible. I once wrote that if the powers that be knew what internet and asymmetrical cryptography can achieve, they wouldn't have ever opened the floodgate of the internet. So what other dogmas do you think they are going to be broken in the future, or strong beliefs that are going to be broken in the future?
I have nothing. I'm sorry.
We should wait
I mean, obviously, I feel like you're asking me of some sort of like mathematical strong belief. Or
not
something.
mathematical strong beliefs about mathematics that are strong. Because if it is mathematical, it's proven.
Well,
It's not going to be to break. But if it is some belief about mathematics, can you think of any?
well, okay. Maybe this was probably not what you were asking about, but I heard it mentioned on some podcasts, and I think it's interesting, so I'll mention it. Maybe one of the beliefs is that serious mathematics can only be done at a university, and or in a university setting, in a traditional academic setting, and maybe that could change in the next 20, 30, 40 years. For one thing, the you know, there's this guy, like I already mentioned, the 3 blue, 1 brown, or 3 brown, 1 blue. This guy with the YouTube channel, he got a undergraduate's degree in math.
A few moments later.
All right, so basically what I was trying to say is I think that this 3 blue, 1 brown is making very serious contributions to math through his YouTube channel. Even though it's just a YouTube channel, he's not employed at a university or anything. He has a Patreon, and I guess he just works from home or something. But like, giving new explanations of known results, uh or alternative explanations, giving like a video explanation in addition to just whatever's out there in the textbooks. I think this is a serious contribution that makes the knowledge more accessible, right? Because mathematical knowledge, mostly, like when you ask someone what it is, it's just like some words written in the textbook, right? That's the knowledge. It's written there. But the fact that he's presenting this knowledge in a new video form, I think this is a serious contribution. And then more generally, um, uh, the thing that I heard on this podcast was that, like, uh, I guess it's starting in the US, that because Trump is destroying a bunch of universities, well, you know, there's this battle between Trump and universities and the funding and everything, and it looks like, at least in the near future, a lot of universities will suffer from a lack of funding, and there's going to be this question of, like, we clearly need math and mathematical research in the modern world. It's becoming more and more scientific. We're getting more technology, dealing with big data. All of this stuff requires math. So we still need the math, but it somehow could be seen as being like too expensive to do it in a university setting, because the university has all of these other costs. Which, okay, I don't want to spend 20 minutes on universities, but like, we can imagine there's a lot of costs to having a university other than the salaries of the professors. And the point they were saying, or the conjecture that I heard from this All In podcast, was that, like, maybe they might just have to make new non-university places to do math research, because we still, okay, they weren't saying math, they just meant like academic research, science research in general, right? Like physics, chemistry, biology, all of this stuff. But we need the science research, and if for whatever reason, whether it be some political reason due to Trump, or just like the inefficiencies of running a university in the US or anything, if it's too expensive to do it in the university, uh they might just make a new non-university place to do it. And I think that could be the next big, I forgot what your question was, but the next big change, or big change in the view of like how mathematics is done. It'll just be done at some private institutes, maybe something similar to Bell Labs that used to exist in the past.
I can actually see it easily happen. I can, because in software we have open source projects.
Yeah.
So science used to be kind of open source, but then we have these journals behind paywalls and stuff. And I think it is a good thing if I see that universities go away, the way that tech companies do not care much about your degrees. They care about how competent you are in your field. So it becomes like that people can discuss math on something like the GitHub for software, that they can make the changes, make their own contributions, and make their discussions. So then math can transform like that. And even in the world of Bitcoin, I can see something like that happening when they are talking about cryptography, the new things that they discover. They are contributing to Bitcoin, but actually it is a contribution to mathematics too. For example, quantum resistant algorithms and stuff like that, quantum resistant cryptography. It's starting from something open source, and it is math, and it goes to math, and it's not made in university. So I think that is a future that is being formed right now, even.
Yeah.
Sohail, it was a great chat, and we were flatmates for 3 years. I always had this idea, but when
You're gonna go with 3 rather than 2?
we know each other for 3 years. We were flatmates for 2 years, but we had so many opportunities. But you come to grasp that opportunity when it is going to be lost, and you're going to China soon. Wish you all luck, a lot of luck with your new adventures, and thank you for today.
Yeah, it was fun. Thank you as well.
Yeah.